Okay, hi everyone. So our topic today is a slightly unusual one. We have been talking for a while about metamathematics, and let me explain why I'm talking about metamathematics. Basically because the structure of discovery in mathematics seems to have a bunch of detailed formal similarity to the progress of time in the physical universe. It's a very bizarre connection. So what I'm interested in is essentially physicalizing metamathematics, physicalizing, understanding in physical terms this process of the progressive discovery of mathematical theorems and so on. And so just like you do empirical science in the physical world, so somewhat bizarrely, you can do empirical science in the mathematical world and try to explore questions like, so part of what's going on is just as we have essentially a model in physics for how we interact with the physical universe and things like reference frames and going at fixed speeds and things like this. So similarly, we're trying to make a model for how mathematicians interact with kind of the progress of mathematics. And in some sense, what we're talking about in the end, well, let me show an example here. That's not an example, but I'm going to show an example somewhere. Well, here, I'll make an example. How about that? So the way we're thinking about it, and there are a couple of different things, and I will want to talk about this later here. The way we're thinking about it is we have, we might have something where we say something like this. We think of these rules as being axioms, and then what we're saying is that with this axiom system, with A going to AB, BB going to A, with this axiom system, the true theorems say things like AB is equivalent to ABBB because there is a path from AB to ABBB.
I see.
Okay, so that's kind of the model for mathematics, and we can look at, for example, if we look over. Let me show an example here, which I've shown a few times before. But
so theorems correspond to paths?
That is correct. Yeah, theorems are paths.
Okay.
And it's a little complicated because there are two complementary models, which I actually would like to talk about for how to think about the structure of mathematics. So this is a typical theorems correspond to paths. Here are some axioms for logic, and there's a path that proves that P NAND Q is equal to Q NAND P. Okay, so that's model number one. So then a theorem here becomes the two endpoints of a path. And so, for example, let's say we want to add the theorem AB is the same as AA, for example. So we can now add that theorem. We can add a lemma essentially that says AB is the same as AA here. So now when we've added that lemma, the proofs of certain theorems, it better be the case that we don't prove any new theorems. There's nothing new that is established by that statement because that was already true, so to speak. But right, certain things become faster to prove, right? And in the system, the only other thing which is a tricky business is we didn't start from all possible initial states. So what we want to do ultimately is we want to find all possible paths here. But that sort of requires that we start from all possible initial states. That makes sense? Because we're trying to find, we don't guarantee in here that we generate, I mean, I don't know whether we generate all possible things. So there's always a question, did we generate all possible LHSs for our candidate theorems? Because once we generated the LHS, with the left-hand side, we're guaranteed that we will find any valid right-hand side by the construction. Does that make sense to you?
So the edges that do get constructed are the right-hand sides?
Exactly, because what we're saying is each theorem here.
But so we're starting from A, and these are the theorems that can be proved from A, and you're
Well, it's not from A because it's not deduction. See, that's the point.
So
That's what's
it's
confusing here.
the theorems that A is equivalent to some formula.
Exactly. Those are that's what we've got here. And if these were equalities, then these would be two-way edges. Okay.
Okay.
So I mean, we could do that. We could show the equality case here by adding to this. I don't think it works with two-way rules. It's supposed to, but I don't think it does. No, it doesn't. But we could just say join this to this, and now we'll have, I have to say, okay, so now we've got two-way connections there. But see what I'm saying? Those are equalities.
Kind of confused if, so like a path from A to AA is a theorem that A is equivalent to AA.
Exactly.
And what does the reverse edge mean?
It's just also equivalence in this case. In other words, in this case, so usually when you think about mathematical theorems, you think about equality. You could as well have something where you could have a different operator there instead of equality, which was a one-way operator. Okay, and that's what this would represent.
Would it mean implies in that case?
Unfortunately, it doesn't quite. Okay, I don't think. It's close, but there's a bit of a complicated mapping to the modus ponens way of doing logic. If we were going to talk about this, we should get Matthew.
I'm on it.
Okay.
So it's like the theorem is like a statement that AA is reachable from A.
Yeah, right. But look at this case here. This is axioms for logic. Okay.
Mm-hmm.
Axioms for logic, and this is proving a theorem that something is equal to something. See what I'm saying?
Right.
So that's exactly okay. So similarly, when you have an algebraic system like a group, for instance, these things here could be like the relations in the group, and these are like words in the group. Make sense?
Yep.
So in fact, with this particular way of dealing with strings, strings are automatically associative, right? String concatenation is an associative operation. So this thing is born as a monoid, actually. Doesn't have it depends whether you think it has an identity or not. But it's basically born as
makes sense.
And now every time we add one of these relations, it's like adding the relations in a group. Okay, and this whole cluster is words that are equivalent to a given word. So it's it's complementary to the Cayley graph. The Cayley graph is saying, consider all the clusters here which are distinct from which represent distinct elements of the group, because everything in this thing represents an identical, represents an equivalent. They're just different words that represent the same element of the group. Make sense?
Yep.
Okay. So, okay, I'm just going to add something which confuses me a bit and might confuse you, and may or may not be relevant to the main thing we're going to do here today. Okay, so this is one model, is we're thinking about equivalences, okay? And that's the story. Now, a different model, okay, so let's take a look at a couple of other, by the way, I think Ian has lots of strange scraping noises. How they went away, but Okay, so I want to show a different way of modeling what's going on. And the different way of modeling what's going on is, okay, an equational multi-way system. So an equational multi-way system here is just saying, here are a bunch of equalities, okay? And to derive a new equality, you take two existing equalities, and then you simply, let me find my version of this. Hold on. Okay. To derive a new version, you are simply saying you're taking x, y, u, v, right? You're taking two pairs. Okay, so this is like you're deriving a new theorem from an existing theorem by applying another theorem. Does that make sense to you?
Yes.
Okay, so the graph we get there will always have two edges. One of those edges will be, I thought I actually had a version of this that has some, one of them one of them should really be a dotted line because it is the use of an existing theorem, okay, on a theorem to derive a new theorem. Now notice that our standard theorem prover has something which looks very similar to that. Okay, but our standard theorem prover is essentially following just one path through here, right? It's generating one proof. This is showing all possible proofs that work this way. Does that make sense?
Yeah. So what do the edges in this?
Okay, so the edges
mean?
represent, okay, so they really should be two different. I thought I had done this actually here, and I'm a little bit confused by this. So maybe I did it in here. Oh, here we go. Here we go. This is a better one. So let me just pull this over here. Okay, so here I've got to every node here, there better be, unless I'm confused. I'm a little confused by what's going on here. Maybe there's an arrow coming in there that I'm not. Oh, there's an arrow. Yeah. Sorry, I didn't see. There's one solid arrow comes in.
Mm-hmm. And that looks like it's applying the first equation that AB equals BA.
Yes, so there should be a dotted arrow coming in there, right? The dotted arrow meets with the solid arrow to produce this result here.
I see.
See what I'm saying?
Yep. So you could transform either the left or the right hand side of an equation with
exactly
other equations.
Exactly so. And that's exactly what you see in the code here. It's just giving two cases, one in which it splices into the left and one in which it splices into the right. Okay?
Yep.
Okay, so that's because it's an equality. You probably do the same thing without equality here, with something that's a little bit more like, okay, so one of the weird things here, this is, so I guess like there's an analogy here to category theory, but these are now symmetric categories when it goes both ways. But I think you can do the ordinary categories going one way. I think that's the analogy with what happens without the two-way arrows here. Okay, so so now let me just remind you, a proof here is a single path. There may be multiple proofs that AB is equal to ABA, for example, right? There are multiple proofs. There are multiple paths here. Each one of those is a proof. And I have a pretty decent thing that is called find string replace path, in which I give it. Okay, so let's say I want to prove that A is equal to AAA. Okay, I just say like that, and it will give me that path. And that is a geodesic path That is at least one example of a shortest path that is the proof that A is equal to AAA. Okay, and I could annotate this proof by saying what was the actual move made at each step in this proof. Make sense?
Yep.
Okay, so here the proof is a little bit more elaborate to give, because the proof will say, just like these proofs do, they say, I'm going to use certain lemmas to apply those lemmas here to get a new result, to get a new theorem. Okay, makes sense? All right, Michael on our live stream is asking about computational irreducibility. The way that comes about is very, very simple, actually. If we want to know the answer to the question, is A equal to, I don't know, AAA, there's no upper bound on how long a path we should have to follow here. It's a sort of irreducible computation. So for example, let me try asking this. I may hit the boundaries here. Let's say 5 A's. Oh, it found it. Okay, this was quite short. But there are other examples where it could be a very long path that you have to follow to determine that, yes, this is equal to that. And that's the story of computational irreducibility, and ultimately undecidability comes about because you can't know whether you can actually, whether that connection, whether that path exists. But remember, in this case, the way that we add lemmas, this is an example, wherever it was, this is an example of adding a lemma. Lemmas make it faster to prove things, okay? Yep. And here, there's not an obvious way, at least not to me, of how we decide which lemmas to add. In this case here, it's all about adding lemmas, because everything you create is itself a lemma. In this case, in the main multi-way system, the things you create are just terms. Does that make sense?
Yes.
Okay, so here, a theorem is the two endpoints of a path. That's what a theorem means. So the question of how theorems are connected. So for example, if we want the theorem A, okay, so let's look at this for a second. So if we want the theorem A is equal to AAA, right? One way we can get that is to just give this path, okay? And that path, I didn't include it. Unfortunately, this function doesn't do it quite yet. Would give which axiom / lemma was used at every step in this path.
Yep.
Right. Okay. But now, let's say I want to make this more efficient, and I want to say I'm going to add in this lemma that says AB is AA. Okay, so let's look at that one there, and then let's say for this, let's compare them. We'll say, actually, let me compare. Let's do this theorem here. Okay, so A is equal to AAA. Okay, that's that case. And now let's do the case where we've added the lemma AB is AA. Okay, so now let's see what the proof is in this case where we've added that lemma. Okay, we got a shorter proof. Makes sense?
It does.
Okay, so effectively we have for a given theorem, I guess we could make a network, and we should figure out how to do that. We can make a network that shows for every theorem how that is used in the proof of another theorem, right? So often with the axioms, we're just using axiom, axiom, axiom over and over again, right? Okay, why am I telling you all this? Okay, so I am trying to do empirical metamathematics on the most famous collection of theorems in history, Euclid's theorems, okay? And so, let me show you something. So what I'm trying to do is I'm trying to map what happens in Euclid. So in this case, there are certain lemmas we could choose to use, and we would have certain relationships between those lemmas and the final theorems we prove, okay? Now, why am I doing any of this stuff? Because this building up of lemmas and the maintenance of lemmas turns out to be equivalent, I think, to causal edges and energy in physical space. And So it's going to turn out that bizarrely, you get things which are the direct analogs of black holes in this metamathematical space that are the result of sort of having too much energy, too many lemmas built up. So I think the way that's going to work, and maybe actually I noticed Matthew just joined us. Maybe he has an opinion about this. The thought would be if you add too many lemmas, you will get a space-like singularity, which means a space-like singularity means that essentially the system terminates, or at least some part of it terminates. Do you believe that, Matthew, or do you? I mean, the question is we get lots and lots of lemmas here. We are jumping ahead further and further. And the question is, what then happens to this system? So for example, in this case, we could look at the growth rate of the number of terms we reach. Okay, and we can look at it again here, and we can ask, how does that growth rate vary with the number of lemmas we have?
I've got one analogy. In geometry, you get two triangles quickly, and then you can define the center of a triangle, and then things get weird.
Yeah.
Because there's over 25,000 known triangle centers now, and we keep finding more and more.
Well, I'm not quite sure I understand that, but we can talk about how this relates to Euclid, but I was talking just purely about these things for a second. And someone was just trying to speak up. Was that Shelfan?
Oh, no, that was actually me.
Okay.
I'm not convinced yet of your claim. You have to do some more work to convince me.
Which claim?
Your claim that if you keep adding lemmas, you'll basically get a black hole.
I'm not sure it's correct. Okay, I'm not sure it's correct. I'm also, the other set of claims have to do with models. So this is not coordinatized. That is, well, let's not go there for right now. That's a separate branch. What we're mostly talking about now is the dependence of one theorem on another theorem. Okay, so this is giving me the derivation of terms. This is giving me directly the dependence of theorems on theorems, if I'm not mistaken. Does that make sense? Right, because here, but I've got two kinds of edges. I've got the dependence, the derivation. I don't quite understand this, and maybe Matthew can help elucidate this. We've got the core theorem, or maybe Peter can. We've got the core theorem, and then we are using another theorem to derive a new theorem. I mean, I think it is really just using implication. Is that not correct?
Or is it substitution? Basically just using substitution.
Well, it is just using substitution. Another, yeah. It is using substitution. But how should I think about this? Because I mean, see, in this case, I've got this whole, here, I've got a limited set of, I can derive everything from the axioms. Here, I'm sort of implicitly getting lemmas because I've got a bunch of paths in this graph. Here I'm explicitly getting lemmas because they are the nodes in my graph.
Right. The two sorts of graphs are related. There's a relationship between the two. I think one thing that you can do one way, you can also do in the other graph, and vice versa.
Well, because in this graph, every path is a node in this graph. Right.
Yeah. And any let's say finite path going from one node to another node in the left graph is a node in the right graph, correct?
Right, but what are the causal edges here? What are these edges? I mean, so in other words, or is it the case that? Well,
a lemma can be understood as just another path in this graph on the left.
Exactly.
And so what you can do is you can take a specific path in this graph, and you can sort of substitute that path in to a node in a string. So basically what it's doing is it's giving a way of taking a specific path and extending it by applying another path. It's sort of like chaining two paths together is what it's doing. It's taking two paths in this left graph and chaining them together.
Well, in other words, so you've got sort of a freeway here. If we've got a lemma that AB is ABBA, that becomes a single jump.
Correct, yeah.
But you see, whereas here we are progressively building up lemmas, here it is a separate choice to add lemmas.
Correct, yeah. So here the lemmas are almost invisible. What you've basically done is you've taken the proofs and you've expanded them all out, so they're just using the atomic axioms, and you aren't actually seeing the lemmas. Although you can begin condensing this graph, creating the graph on the right, where you actually have lemmas.
Do you believe that to be the case, that you can condense this graph to this one?
Oh yeah, definitely.
I agree.
But okay, so let's figure out how to actually do it. So then how do the causal edges, how do these edges that represent the use of another lemma show up here?
I would think instead of chaining them, really you're inserting one chain into the other.
That's what I mean when I say chaining, exactly, yeah.
So to take a concrete geometry example, the two theorems that give you the theorem that intersecting chords have this relationship about you multiply them together and you get the same number. To get that, you would use the theorem that two triangles with that share the same side.
Okay. So some various other theorems. Yep. But so right. So I mean, look, if we want to see where we're going with this, okay, let me show you something about Euclid. Okay, so let's see whether I have this here.
Let me mention something about Euclid. He goes into measurements and with that accidentally establishes number theory and the elegant proof of infinite primes.
I'm aware. Okay, so look, this is, let me show you this. This is the network of theorems in Euclid. Okay, and this is what I've been looking at and trying to understand. And this is what I really wanted to mostly focus on here today, but I want to understand where where things are coming from and going to here. So what this is this says that, for example, in one result here, let's pick a result here. So let's say, okay, so here, this is theorems in Euclid. And now let's say, so this is a graph. So let's say we want to say vertex out component of Euclid, comma, book 1, proposition 7, let's say. I'm picking something at random. Okay. So let's say the one step out. Oh, I meant resource data there.
I think you want theorem 7.
We are very confused about that. We need to straighten this out. We need to straighten out this representation relative to the representation we're using in the entity store. We either need to change the data repository entry or we need to change the entity store. Okay, so I don't know why there's a none there. That's really odd. But so what this is saying is that book 1, theorem 7 depends on common notion 5 and theorem 5 and postulate 1, right? And so now if we go another step here, we'll eventually boil down to postulates, right? So if we make the whole thing, we would basically say, let's go to infinity here for just that one thing that's pretty early in the book. By the way, is it true that Euclid never forward references? In other words, Euclid is always progressively building. Every later theorem in Euclid is refers only to earlier theorems. Is that a true statement?
I'm not sure if it was that way originally, but it became that way.
Okay. All right. So what we're saying here is that book 1, theorem 7 has this collection of dependencies, which eventually, so this should go down purely to, eventually everything should come down to postulates and common notions, right, guys?
Right.
What I would expect, yeah.
And we should check that that's true. So let's see, how would we do that graph theoretically? How will we check? So there are a couple of things to check. Does Euclid only back reference and not forward reference? And second, does every theorem eventually depend only on postulates and common notions? Okay, so you can see why I'm trying to understand in this modeling. So when Euclid says that, theorem 7 depends on, okay, these are essentially axioms, right? But Euclid is saying here that to prove theorem 7, we use theorem 5, right?
Yep.
Okay. So the question is, what is the interpretation of that? So what that's saying is, in wherever it was, in this setup, to say theorem 7, so one of these might be theorem 7. I'm a little confused to what the direct analogy is. So to say we use theorem 5, in this case, we don't need to use anything. We could boil everything down directly to a bunch of uses of the postulates and common notions, although there might be many, many, many copies of those. So let's see how that works. Let's look for Euclid. If we wanted to prove any theorem in Euclid, we could do it by enough steps of postulates and common notions. Do we agree?
Yes.
Yes.
But the intermediate theorems are purely for convenience, right? Just like here, we can prove any theorem by following the whole path, but we could shorten that path by throwing in some extra lemmas.
Right. Particularly one like side angle side, which Euclid uses extensively.
All right. Well, we'll find that, and we'll find what it means for him to use it extensively, because we should find a centrality measure in this graph, right? That's what it means for him to use it a lot.
Right.
Sounds right.
I mean, we could literally just do.
It would be a high in degree, right?
Yeah, well, let's rank them by, well, not necessarily, because the question is, does he directly use it? Okay, so let's ask, which theorems are most popular used directly?
I'm
Okay.
going to guess a measurement or side angle side.
All right, we will find out. Okay, so let's go. And by the way, we're about to, we should combine the entity store version of this with this network here, so that you can ask for the entity store which theorems Euclid used to prove a given theorem. Does that make sense to you guys?
Yes. And Shofan and I have discussed that. Basically, we'll just have to add some entities for the remaining propositions and common notions.
Right.
Some
And
of
also
them might not have geometric scenes associated.
Yeah, I understand, because they're
with
not
our
geometric
statement.
propositions.
Yeah.
And later we'll do that. I mean, right now it's just missing, not available, or not applicable for those. Okay, so let's drum roll here. Let's find out. So let's say take, what do we want to say? We want to say take largest by a vertex list of EUC, comma, vertex in degree of EUC, comma, hash.
Yep.
Let's take the top 5. Okay, book 10, theorem 11. All right. Now, I did have a little bit of code that converts to the format for, where is it? Gosh, I have no idea where it is. Maybe I had it here. Oh, I don't think so. I'm looking for a piece of code to convert to your version of how you look up Book 10, Theorem 11. Well, let's say,
So
how would I do it? Can I do a control equals?
Yeah.
What do I say? Euclid Book 10, Theorem 11?
Theorem should work, but proposition.
Seems like you got some linguistics to deal with there.
Currently don't have that in the AP table.
How should I type this in? You suggest?
Oh, I see. Yeah. So this proposition isn't in the EP table.
Ah.
Yeah.
Ah. Okay. All right. Okay. So I want a. Okay. So I better have my function. I had a little function that converted to your form. Well, let's do one that is, so that I can see. Hold on a second. So if I say,
1 Theorem 3 is definitely there.
Which one?
Book 1, Theorem 3 is definitely in the EP table.
Okay. Euclid Book 1, Theorem 3. Drum roll. Come on, the drums are still rolling here. That is a very bad result. Okay, work to be done here. Okay, so let's go ahead. Shoot, I need this converter. Hold on a second. I just wrote that converter, but I can write it again. Actually, I think I called it. And this is, by the way, telling you something about how maybe what we should do is put into the data, it might be easiest to put into this data repository entry the information on the entities here, maybe, not certain. Okay, all right, so anyway, what is your representation of, remind me, this is geometric.
So it's
right?
entity, geometric scene.
Okay, well, hold on a second. Let's take this, would be something like book B theorem T goes to, now what? Colon equals entity, geometric scene.
Yep. And
Now
string
what?
join Euclid book, comma B.
Actually, you know what? I'm going to use the string template here.
Okay.
B followed by what?
Proposition.
With capital P?
Yep.
Okay.
And T.
Okay, and I just apply that to the list BT, correct?
Looks
Okay.
right. The string template, does that just need to be one string with no commas?
Oh, no. It's a much stupider thing. Yes, it needs to be one string with. What did I do wrong here? Hold on a second. String template. Oh, yeah, you're right. You are absolutely right. But that shouldn't be doing. Okay, so this has no spaces, right? Oh, yeah, that's the problem.
Yep, that's correct.
Okay. All right. So EEC, let's say we're going to say book 1, theorem 3 here. What? Oh, double tick. What the heck? I am very confused by this.
Should it be theorem proposition?
I don't use string template a lot. I'm not sure
Well,
why it's inserting like that.
I could as well have used string join with all that trouble. There we go. Finally, we got that. Okay. So now here we can say statement, right? And presumably we can say here seen.
Yes.
Okay. And so now if I say random instance of that, I should know what this is about. Well, I don't know what that's about. To cut off from the longer of two given unequal line segments, a part equal to the shorter.
Is this 12.2?
No, but I could run.
Yeah, can you run the random instance in 12.2?
Prototype build or regular build?
I think regular.
By the way, I wonder how many times those things actually get used. Let me just find that out. Okay, so you say run this. What exactly am I running? I'm running random instance of that scene.
Yes. Yep. So now you can start with step 1.
What are you telling me? What do these mean?
So this is a construction.
Why can't I resize that? Complaint. I should be able to resize that.
I'll pass that along to Dan.
Okay. But so this is, I can think of this as part of a proof then, that this fact you've got multiple steps in the construction is like a proof. Is that right?
Yes.
Yes.
So you construct some things, and then the conclusion is that the thing you constructed satisfies some property. Like you constructed line segments with equal length, or what is this one?
Okay, so to what extent can I think of that kind of construction as being like my way of establishing from whatever this leads to this? Is that like that, as opposed to being an equality type proof, or is that something different?
Peter, do you?
I would say that's more like the one in the other notebook where there's a pair of edges leading to it in each step.
Okay. I'm not quite getting that, because this looks like it's a 1, 2, 3 construct. But you're saying you're feeding in something. You're feeding in, as each step in this construction goes forward, you're using some other theorem to do the next step in the construction. Is that right?
I believe so.
Okay.
Not sure.
We're at
Right. So like if you have 2 points already, then presumably one of the replacement rules would be you can create the line through those 2 points.
Okay. Let's just count the number. Let's see. So we want to know what is the in degree of each of these things, right? So we want to say vertex in degree, you see. Wow, that's a lot of uses. Wow. So actually, let me just do the following thing in terms of direct uses, okay? Just because I want to see what, let's just get the, well, here we could just say vertex in degree / at vertex list of Euclid, and then we just literally say histogram of those, right?
Nice.
Looks like
But I'm confused because this is saying, okay, there's 120 that get used only once. Let's just make this a histogram with oh wow, there are 120 that never get used. Okay, and if I now go, so let's do, anybody remember how to do this probability histogram with log. Is this log? No, count. Interesting. So that's showing in Euclid, that's showing the distribution of frequencies with which theorems get used, right? So there's a big winner there, and then there's ones, then there are the ones down there.
Mm-hmm.
So actually, one thing we could also do is to look at the Euclid network, and we can ask for the n degree, and we could display a vertex size that's proportional to the n degree. Right. So let's take a look at that. So if we're asking, given the full, so the full network of Euclid would be. So actually, there's so many questions here. I mean, we're going to get. All right. So this is. Let's just do that. Okay. So let's say we've got the Euclid network, which is a UC, right? As a big graph. Okay, there it is. Now that's a big mess. Now, what are we going to do to organize this graph? So first thing we probably want to do is to identify the. I mean, it should be the case that if we layer this graph. Actually, I think Charles told me. Let's see what version this is. It's old. August 14th. It's 4 days old. Charles said he put something in where you could give multiple nodes. So what I want to do is to put this on a floor of the postulates and common notions and see how tall you build from that. Does that make sense? Because my question,
yeah,
how would I do that? I mean, in other words, in this picture, I could just say, go ahead.
Try using graph layout goes to layered digraph embedding.
I did. Yeah, I did that. So I can show you what that produces. That won't work because that would be a, actually that one thing I could do is reverse the graph. That will help. Yeah, okay, that was uninspiring. I think it might help to reverse the graph because that way I'm in the layered digraph, I'm hanging down from the common notions and so on.
Yep.
Okay, because here, presumably, I'm hanging down. Who knows what I'm hanging down from? But let's reverse the graph. Okay, but unfortunately, this is probably going to hang down. I don't know what it's going to hang down from. It might be hanging down from. I mean, it's got 10. Well, it's a little bit better. It's not hugely better. So what is this saying here? This is saying, assuming that these are common notions, which I don't actually know, but let's assume that. Maybe we should color the common notions. And to do that, what we want to do is vertex list. Let's say vertex size arrow if length of hash goes to, if length of hash is greater than 1, actually I'm just going to do, you know what, I'm going to say vertex color. Why is that doing that? Why is it going red?
Maybe just because you haven't closed off the...
No, I don't think so. Vertex style. Okay. If that's greater than 1, then let's say blue, otherwise red. And then I want to map that over vertex list, VUC. Okay, and I may need to increase the vertex size. Come on. What is this doing? Why is this taking forever? Okay, useless. All right, let's say I'm really shot in the dark, vertex size 2. This may be just covered in giant circles. I don't remember what the definition of vertex size is. Does anybody know?
No.
Well, let's say vertex size.
I always rely on the documentation.
Well, you could look it up for me, but okay. But I think I'm seeing that there's red at the top there. So this is basically there are 476 theorems, I think, in Euclid, and this is showing. Here we go. Okay, dandy. All right. So what this is showing then is those are the postulates starting off there, and this is then showing the flow of theorems coming from those postulates. Make sense?
Yep.
So essentially what we're trying to do now is to ask how similar to a simple multi-way system was old Euclid, right? Because this, okay, so the other thing we should be able to do is we should be able to degenerate every theorem to its constituent. So let's take a theorem. Okay, so let's decompose a theorem. Decompose into purely the action of axioms. Okay, so let's take a theorem. Take one theorem. What do we have here? We had, let's take, I don't know, which one of these is in the geometrical area, so we can.
1, 3.
Okay, 1, 3. It's not going to be that interesting because I think let's find out. Let's find out whether Euclid only back referenced. Okay, first thing to do.
Okay.
Okay. Okay, so for that, what we have to do is for every element, what we need to ask is, so we need a partial ordering, an ordering function, Euclid order, in which we're saying, given a book, well, actually, what we want to do is we want to say, well, it's proposition 1 and proposition 2 says, if it's kind of a mixed radix arithmetic because the book is the
Yep. So
the
lexicographic order.
Yeah, actually, Richard on our live stream is pointing out something interesting, which is the Metamath proof database. What is that? Is that the Mizar project thing?
it's related.
Is it useful? I mean, because that thing was horribly non-useful back in the day. Is it? I mean, are there actually non-trivial proofs there that are interesting?
I think so.
Because this is a good other. Well, that's interesting. Let's look at this. I mean, because can we ingest these proofs?
In principle, or do we have something to do it?
Oh, in principle. I mean, I don't know. What is there a proof here? Let's take a random proof. What is this? In what format is this? What is this?
And
I wonder whether this has a dependency graph. Is this in fact a proof here?
I've tried something similar like this before on the Lean library. Like import the entire library as a graph, and then you have edges
Yeah.
between, when they get used. MathLib. That's
How big is the lean library at this point?
I don't know.
But we already have that imported, yeah?
Yeah, so a while ago, Rob created a dump for his thousands.
What is the status?
16,000 definitions, 34,000 theorems.
Oh, I want that stuff.
Yep.
That's a good suggestion. Thank you, Richard, on a live stream for this. I really hadn't looked at this in probably 15 years.
One item of comparison is Euclids usually are not optimal, whereas Metamaths usually are, since they're computer generated.
Are they computer generated? Oh, wait a minute.
I think so.
Your claim that they're optimal is simply, I mean, look, I've been looking at the optimal proofs of various theorems by just enumerating multi-way systems, and our theorem prover is certainly not optimal. And it's state of the art in terms of equational logic theorem proving. So I just don't think I don't think you can get the full tree walk. It's really hard.
Oh, let me rephrase that for simple theorems.
Well, so who's behind this project, by the way? Is it still the same people as the Mizar people, or is it completely different?
Don't know. Let me see.
It's a mystery. Okay. But so when you say, this says hypothesis here, so is that's another theorem? No. Oh, that's using this result, right? Is that right? What's its rule of inference is the question here. So SWSH on a live stream is implying that this is a very simple process in terms of theorem proving. But what is it actually doing? Go ahead.
I mean, this is a guess, but maybe ref is the lemma that's being applied to the arguments 1, 2, and 3, or.
Well, but this seems to be the hypothesis here. And you think that this is, well, I'm a little confused about it. What's rules of inference are?
Click on one of the refs.
I did that already.
And oh, I see.
Well, actually, this is very encouraging. This is more data. This is going to be a lot more data. If only we can read it. Is there a machine readable version of this? Oh, structured version. There we go. Wow. That is disappointing. Oh no, terrible. How can the structured version be absent? No! Help! Well, that's not good. Okay.
They seem to list Mizar as another group. Doesn't seem like themselves.
Okay. Although with these logicians, you never know.
Mathematica program to generate arithmetic proof steps.
Where? What?
listed under other MetaMath related software on their site. It doesn't.
Okay, well. Okay.
Inference are probably just sentential logic and the most basic first order logic, instantiation. I forgot what they are.
Well, but they're essentially structural, is what you're saying.
Right.
Okay. All right. Let's go back to Euclid for now. Okay. And let's see. So by the way, in this case, for example, they're definitely using the idea that you only back reference, you never forward reference. Right?
Yep.
We really should have a way to ingest these. I mean, it's this looks like a very interesting database. See if there's anything useful on its homepage. Oh my gosh. Okay. It had a Google group in 2016. That's not a very good sign in terms of how we can find out. Wow. Well, this is cool. This has advanced quite a bit since I last looked at it. Okay. Well, great. More raw material for my efforts, but we need to figure out how we get the structured version of those proofs.
Right.
Okay, that's some reading material for me. All right, let's go back to Euclid here. Drat, this project of mine is getting more complicated by the minute. Here I was just thinking about, basically what I'm trying to do is understand metamathematics in bulk. And you guys just fed me another 34,000 theorems to look at. I thought I only had 467. That's all the better. More bulk. I mean, we believe there are about 3 million theorems that have been published in the literature of mathematics and history. Okay. All right. So, oh gosh, how do we do this? This is really tiresome. This is book, arrow B1 blank. What was it? Proposition? Was that what this was calling it?
In yours, it was theorem arrow.
Okay. Okay. Colon equals, let's see, B1 less than B2. How do I get this ordering? And, is that right? T1 less than T2? All right, and if that isn't true, then, okay. Meanwhile, Euclid order of, bluff, quaff, horrible mess. What a horrible mess. Association / at length of A equals 1 less than 2. A blank.
So it needs to be less than any book.
Yeah. So this is saying, let's just say that order is always true, right? Wait a minute. This ordering, hold on, this is wrong. This is wrong. This is because it wants to be 0, -1, and 1, right? To be an ordering. Well, okay, well, this, I guess, would just be true. Right? If either of them is less than, actually not, that's not A, that's AA. If either of them and that one is false, right? Am I right? I don't know if this is going to be consistent. How do I want to do this?
You need to restrict AA to have length 2.
But then how do I compare a theorem to a theorem? You know what? This is silly. This is silly. This is the wrong way to do it. Okay, I've got a much better way to do it. Vertex list of EUC. Okay, I'm going to say map indexed. Look at this. This is a much better idea. See? Key is that. Ah, wrong thing. Okay. Oh, why isn't that in order? What the heck? Well, I mean, probably if I do a sort on vertex list, it will put it in a not totally stupid order. Oh no. Crazy. All right, okay. Let's just be very, very hacky here. And I do want to find out what that none is, but I'm going to be super hacky. I'm just going to make this be, because I can't be bothered to sort it any other. Oh, actually, you know what I could do? I just say sort by vertex list length. That should work correctly. Okay, now we've got something reasonable. Okay, so now we'll make that into a key. Okay, so now all we have to do is say, for our original thing, we just say the list of edges, right? Just say edge list of EUC, right? That's going to give us all the edges. And then we want to replace that with key, I claim. There you go. Right? Then all we need to know here is if I compute these numbers. So actually an interesting question is how far these jump, right? So if I simply do list triple at that, and then I say list plot that, that's going to show me how far they jump. Ooh, Coolosaurus. Okay, so does that make sense? That is asking for a given theorem, how far back does it refer? And notice that we can already see from this picture that he never forward references. Make sense?
Yep.
Yes. That kind of became the style in math to avoid those. But we don't know whether Euclid originally was so pure.
Well, we don't. Euclid didn't write the proofs down originally. Okay, but this is a nice thing. So this is showing us the, and so now, let's see. So this is saying that most theorems, actually, we probably should remove the self-reference, right? We should delete cases of, let's say, list triple at this thing here. Delete cases of x blank, x blank. And now I want to say list plot aspect ratio to 1. That's still interesting. Okay, so most of these So they reference very nearby. Did I get this wrong, or is this right? This is right. This is saying the x-axis.
It makes sense that he would
No,
build.
but hold on a second. The x-axis is the theorem that is referring, and the y-axis is to whom it referred, right?
Yes.
So this is saying that it often refers to something very close to it, but
Yes.
sometimes refers back a long way.
Right.
I do believe that this is a more confusing. I'm gonna reverse all of these, unless you think that's even more confusing. That says, okay, so now what this is saying is, and really actually what I want to do is reverse the anybody know how to do that, to reverse the y-axis?
Not off the top of my head.
Well, let's do a hackalola on this, okay? Let's just say -1, 1 times hash slash at this. This is a total hack.
1 minus 1.
Thank you. Okay, total hack. But this is showing us, given how far we've got through Euclid, right? This is showing us where we reference, right? So I was asking, are the steps okay, so there's several points here. Okay, so first question is, are these the books? That's a reasonable question, right? So in other words, when we get up to, whatever we are, about one something or other, let's find out where the book boundaries are, okay? So in key, let's say, this is a hackalola, but let's say first position. This is a major hackalola. I'm just disappointed with myself that I'm doing such hacky things. But anyway, actually this isn't so bad. Book arrow B blank. First position of that, and let's make a table. How many books are there in Euclid? 13. Is that right?
Yes.
Yes.
That wasn't impressive. Did I get this wrong? Take key, comma 20. Book arrow 1. First position. Well, let's do this. First slash at that. Help! What's wrong here? Well, there we go. Okay, so that's the positions of the books. So let's see, around here, around 200. Yeah, we might have a book transition there. Yeah, look, they're around 3. Well, let's plot these. So let's say first slash at that. And now these, we want to mark those. I could mark those as ticks, or I could mark them. Who has a good idea how to do this? Those are x-axis labels, right? Going down. No, actually, they should be on this axis here. Well, they could be on both axes. Oh, how about a grid lines? How does grid lines work? If I say this thing here, arrow, grid lines, arrow, let's say bookmarkers as opposed to bookmarks. And I think I need to look at the grid lines documentation. It's very annoying that that doesn't bring it up.
You could separate them into groups and list plot them, and it'll use different colors. sublists.
Yeah, that's amusing. So I could do that with take list, right? By successively taking ni elements. Okay, so I could do that with take list. All right, let me do both ways. Okay, so bookmarkers, let me just see if that works. No, I need to read how grid lines works.
You could use a group by maybe.
Wait. Why isn't grid lines working? Two-dimensional graphics that specifies grid lines. What's wrong with this? Grid lines drawn at specified positions. List of grid line specifications. Oh. X grid, Y grid. Oh, I see. I think I probably have to do it twice. Okay, well, that is showing us basically, that's showing us where the book, oh, it's kind of interesting. Look at that. That's so there is definitely structure here that is related to the books. And I'm just going to, for the hell of it, I'm going to do your case too. So let's say take list of, okay, so then it will be that. Take list of this thing, comma, differences, if I'm not mistaken, of bookmarkers. Oops. Okay. Why do we have so many fewer? Something went very, very, very wrong here. Something went very, very wrong. We're taking take list. What does take list actually do? I thought take list took chunks of that size. I'm very confused. This take list thing here.
Books 5 and 10 deal with measuring things.
Okay, listen. I don't understand why this plot looks different from this plot. Anybody understand that?
Is it just coloring them along the other axis?
No, look, there are a smaller number of dots here than here.
Oh.
Right, you can see that, right?
Yes.
So that shouldn't be happening. I don't understand that. Okay, let's not worry about that right now. Okay, so we've determined that Euclid only forward references, only backward references. And we've determined, right. Okay, so now we want to break it down into, Brian is asking how many cases were deleted. I believe we were just deleting self-self. Can check that. Okay, and Arash on our live stream is saying get structured versions from other mirrors of Metamath. So somebody's able to paste those mirrors, that would be highly useful. Only for the first 120 entries, which is why. What did I get wrong? Oh yes, so it is. Thank you for noticing that. What did I get wrong here?
Oh, two differences. Do you have to add the first one, maybe?
No, that won't make any difference. There's something wrong with the structure here. Let's look at this. This is what's obviously wrong. Now, I would have expected that this would give us, right, so this is, why are there not the right number of entries here? Oh, I'm really confused. I am really confused here.
So there's 13 books, but you only have 12.
Yeah, but that's because the difference is, oh, the last book is missing, but the last book can't account for that much.
Yeah.
Is it first of bookmarkers that you want there? Or
no, I want the total length, because I want the take list. Oh no, I want it minus the length minus the last bookmark thing. So what I want to do actually is differences. I want to append to this the total length. That's still completely wrong. Okay, let's not worry about that right now. It's kind of annoying, but let's not worry about it right now. Okay, so let's decompose purely into the action of axioms. Okay, so we're going to take this, and we want to see for a given theorem, what would it look like if it was purely done in terms of axioms? So let's see how we would do that here. So what that's saying is, given this, right, given a theorem down here, right, we want to write it. How do we do that? We want to write it purely as a sequence of these axioms.
Take the edge list and make those into rules and then do a replace repeated on the vertex? Does that give?
Let's try. Yeah, it should work. But what about thinking about it graph theoretically? Graph theoretically, it's going to visit this thing many times, so that's not going to really give it to us, is it? So I think you're right that that's a better approach. Okay, so this is the correct way around for EUC. So let's say edge list of EUC. Let's make those into rules. And then what was our favorite theorem? Let's try taking what was the theorem that we were using as the test case?
Book 1, proposition 3, or theorem 3.
Okay. Okay, so let's say this. So now we want to apply this. Okay, this is super dangerous, but let's just try it. That was extremely uninspiring. Is that the only thing it needs?
That's hard to believe.
Oh, no. No. Replace list is what we would need here.
Oh, yeah.
Okay, and then what we want to do is we want to nest replace list a bunch of times to see what we get. Okay.
Yeah.
Fixed point.
Yeah, fixed point list, but I'm not bold enough for that yet. Nest list. So now we want to do this, and we want to say onto book 1 theorem 3, and let's do that like 3 times. You're making a lot of grinding noise. Could you stop that, please, Ian? Okay, so the fixed point is not going to work because fixed point is going to make this go away, right? So that's not in fact what we want. What we want to do is for each of these things, we want to then replace this by its own list, right? Oh, no, this is wrong. Look. We have a different thing here. We want to say this ampersand / at this and then this. What did I get wrong? Okay, so let's look at this. Okay, so this is getting a replace list. How could book 1 theorem 2 not be something that has a pre-image, so to speak? Did you understand what I'm asking?
Right. What's the...
So this should be, I should be able to apply this here to that. And what am I going to get? What are these? What are those things there? Oh. I think I have to say here, yeah, I want to say flatten at the end of this. Flatten that replace list like this. Okay. Okay, so this is claiming now that, oh, this is cool actually, that theorem is basically, okay, did we get it down to the end? No, we didn't. Yes, we did. We got it to the end. And do we believe, no. What happened to postulate 2 here? Oh, it's because there's no self-edge for the postulates, right?
Shouldn't be.
Have to keep those in there.
Yeah, we got to keep those. We got to keep the postulates and common notions in there by giving them self-edges, right? So let's say take of sort by vertex list, EUC, comma length, comma 10. Oops, what is that none doing there? We need to find that none. Could some separately pin the question of where the none is? Well, actually, let's just say position in EUC of none. Great. Position in vertex list of EUC. What does it mean, none? Position 13. What is it doing there? Okay, so that's something we have to find. That's a source bug in the. So if somebody can make a note of that.
Yep, I got it.
Okay, so here. Okay, so let's say. Okay, so those are those things. So these, we want to take these and map hash goes to hash onto those. Right, so those become self loops. Then we want to append that. Okay. So the claim would be EUC rules. Okay, this looks as more like it. Okay, so this is going to show us. Okay, so now let me be a little bit more. This is cool. So this is showing us
duplicates.
No, I don't want delete duplicates. I want to see that this is what,
Oh, okay.
if you crushed it down, this is what the sequence of common notions, right? This is saying how much does each postulate, in the end, you percolate it down with all the sublemmas, how much does each postulate get used in the proof of each theorem, right? So, for example, we could look as a function of position in Euclid. We can look at how many of these there are, right? And so another question is, how long is the fixed point list, right? So let's first of all just do that. Length of fixed point list. So that's telling us how many, right? It's telling us how many steps does it take for subtheorems to get down to purely these, right? I thought this might take a while. Oh, there we go. Oh, wow. That's wild. Why does it take 100 steps for some of these? So that's telling us the amount of lemma use in Euclid, basically.
That last one is the Platonic solids.
Okay. So this is telling us essentially how many steps, if we didn't use lemmas, how many steps we'd have to take to prove each theorem in Euclid.
Yep.
Wow. Cool. Okay. So now we can ask the question for, like for example, how many, let's look at the postulate count. Okay, so for each one of these, we've got a certain number of each postulate in common notion. Actually, we can just do the full. Wait a minute, this is wrong. Oh, that's the number of, okay, so this is number of lemmas, number of axioms needed for each proof. Okay, and this is what we could do now is, I'm being unbelievably inefficient in the way I'm computing all these things, but let's not worry about that. Fixed point list of that. This will now be, okay, so this is essentially the lemma depth. Does that make sense to people? It's off by 1, actually. Right? It's making sense to people? That's the number of, that's the depth in lemmas. To yeah, various people are pointing out we could probably shorten these proofs. I agree, although they've been going for 2,000 years, so one would have thought people would have shortened them by now.
No, they just copy.
What do you mean? They've just been copying for 2,000 years? Surely hasn't somebody sat down and found optimal proofs? I mean, for goodness sake, it's the most famous mathematics in history. Are you serious?
Yes, they have. For example, the 17 gon has been ongoing challenge to get a simpler and simpler proofs, simpler constructions.
So where would we find the simplest proofs of Euclid? Well,
maybe the shorter proofs are less human understandable.
That
possible.
Tends to be what happens with the 17 gon constructions. Then there's a lot of those.
Can you send a link to the 17 gon?
MathWorld has a bunch of them.
What do I find? How do I look it up? 17 gon. Ah! How would I find it? Ed?
Oh, Gauss polygon.
Geometric. How about?
There it is, top left.
Oh, yeah. Okay, where are the constructions? Following construction. Simplicity 53. I see. So in other words, the simplicity measure, what is the simplicity measure here? By the way, did Euclid have a construction of the 17 gon? I thought that was originally done by Gauss.
Right, it is Gauss.
Okay.
There's also the mini Pythagorean theorem proofs.
Well, I understand, but I want to see a proof that was in Euclid, and I want to see that shortening over time. So, I mean, in this case, just to give a sense of history here, this says, okay, so how long is the original Gauss thing? So this goes 53 in 1893 down to 50 in 1970.
Gauss just said it was possible, and it's left to the reader.
I see. Well, can we find the shortening of some Euclid proofs? That would be very interesting. Okay, so wait a minute. Where were we going before this? We were looking at. So this is Euclid. This is what it would take if we were constructing. So, in a multi-way system, basically. Well, I'm not completely sure what this is saying. This is saying if we used a multi-way system, it would take us 662 steps. Is that really the last? Is the Platonic solids the last result?
Yes. And that's one other that's had many other shorter proofs.
Wow. Really? That's I mean that is dramatically longer than the other ones. That's really weird. So how else do we see that? How do we see what is its dependency graph going back down? So how do we figure out, okay, that's an interesting question from Bob there. So the people may know, one of my little life achievements is finding the simplest axiom system for Boolean algebra. And so the question from Bob is, what's the simplest axioms for Euclidean geometry? That's an interesting question. Okay, but how do we see this network of what this depended on, so to speak? Because this is saying what's
vertex
that?
out component.
The subgraph, you mean?
There's the out component that will list all of the vertices that you can reach.
Yes, but that's not right, is it? Because that's going to give us. Okay, wait a minute. What is the? Are you really sure that the very, very last? Let me pull up a Euclid here. I've got one close at hand. Book 13, propositions. Oh, it is proposition 18, isn't it? Is that right? Proposition 18 is the. No. Oh, to set out the sides of the five figures and to compare them with another. Is that really the result that? Oh yeah, I see. I say next that no other figure besides the said five figures can be constructed, which is contained by equilateral and equiangular figures equal to one another. Yep, there it is. Okay. He must have been very proud of that result. I mean, that was okay. So let's think about the out component here. So let's say vertex out component. It's a pity that we know absolutely nothing about Euclid as a person. It is funny. Okay, book 13, theorem. Was it theorem or proposition? I keep on getting this wrong. What is it here? Theorem. 18, right?
Yep.
My gosh, that's the direct proof? Has all of those things in it?
No.
Oh, that's the full out component.
Yes.
But that out component presumably contains Okay, so let's see. What's the length of that? That's only 230. I'm confused. That's a different thing than asking the question. That's simply asking which things are used, but it's not grinding each of these ones down to their sources. See what I'm saying?
Well,
Then we would have to recursively use that, make the out component of these, right?
no, it includes that, I think, but it doesn't count multiplicity for when you apply a theorem multiple times. This is just like the
So for that, I would
hierarchy
have to.
of which
Oh,
propositions.
so you're saying if I
which-
take this and I then take the subgraph of EUC with this thing, is that right?
Yes.
And then I probably want a layered digraph there. Why is the layered digraph?
And
take so
maybe the graph
Reverse
needs to be
bar?
reversed. Yeah.
Okay, so what is this now showing? This is showing from somewhere down here should be the final result.
Yes.
But it's ultimately, it's not very far from the axioms. Wait a second. So I see. So all of these edges here, if we splattered them all out and didn't join these together, that would give us our 660 copies of the common notions and so on, right?
Yeah, I expect.
Right, but what this is doing is it's combining those things there, right?
Yep. You just have a single edge if it ever uses the other.
Right, but so the depth here is not large. The depth is only 4. That is the distance. That's a bit surprising to me. Hold on. Why isn't it the case that what we've got is from book 13, theorem 18, we go to some other thing, which goes to some other thing, which goes to some other thing. How come there are only 4? I see. What must be happening is that the minimum path depth is quite small. There is a long path, right? As there's a long path to get from here down to the common notions, but there's also a side path that's quite short. Does that make sense?
Yes.
Okay. So, all right. So what we're learning here, the main thing we're learning is, let's just for fun, let's find out the count of how many times in this giant list of here, I just want to find out how many, what the popular, let's look at this. I'm just curious about this. As we go through Euclid, right, how does the number of uses of each common notion vary, right? So what we want to do here is we want to count. Let's think about this. Let's see where were our things, which were the okay, let's make this list here. This is let's just make a list called axioms. Yeah, Brian's saying compute the minimum maximum path lengths. I don't know how to compute the maximum path length. That's the problem. I mean, without just explicitly enumerating all paths. Okay, so here we've got the axiom. So what I want to do is I want to say for each axiom in each of those fixed points. So let's say FP list is this. So let's go count. Yeah, let's do this. Okay, so I'm going to say count in, this is kind of a weird thing, but let's say count in this FP list axioms function A slash at axioms, and then for each of those I want to go and figure out that across FP list, and I claim that's going to give us, oh my gosh, why is that happening? Count, let's see, FP list sub 100, let's say. Why has that still got book anything in it? That is not a good sign. Oh, what the heck is that doing there? What's that 3 doing there? That's a disaster. Did I have that in there before? Oh no. Oh no. It's completely wrong. Right, that's limiting it at 3.
It came from the nest list of 3, and then when you added the fixed point, it stayed there.
And okay, so this is wrong. Okay, I was a little worried about that fixed point, and as we can see, that fixed point is in fact not converging here. So let's go ahead and oh dear, let's say fixed point list, and let's give it like 10 there. Oh dear. Huh, not a good sign. Well, maybe it gets exponentially bigger. Wow. Okay, FP list there. So let's just say length slash at FP list. Okay, an awful lot of these did not converge. There are an awful lot of 5s there. Right, so there's some that did converge, but many that did not. Make sense?
Yep.
So if we were to do the same thing, okay, so let's go ahead and do the following. Let's if we say length of last of hash FP list, that will be our better, slightly better version. List line plot, plot range all. Oh wow, that thing's now up to 2000. Okay, so this is our better version of the how many axioms does it take to prove the theorem, right? So one thing we're discovering is the real value of having lemmas, or theorems for that matter. But look at this, look at these are huge. I mean, this is this is grinding it down without theorems, basically. Okay, is there a more efficient way to compute what we're trying to compute here? Is this the size? This is the size of the out component, not accounting for common vertices, right? So there's a combinatorial way of thinking about that. We're just taking, we're treeifying the whole graph, right? So in other words, instead of having a graph where common edges converge, we're just treeing out all possibilities. How do you compute that? Is that some graph theoretic thing? It is, isn't it? Do you understand what I'm asking? I'm asking, we're looking at all possible paths in the graph, and we're asking the question, how many paths are there going down to the common notions, etc. Right?
There's got to be some shortcuts.
What's that?
There has to be some shortcuts because you're traversing the same parts over and over.
Right, exactly. I mean, all it is, it's a recursive thing, right? You look at the bottom piece of the tree, and all you're doing is you're multiplying components as you go up the tree, right? In other words, if you have a subtree that has 10 ways that can happen inside that subtree, you have another subtree with 20 ways that can happen inside that subtree. The combination of the two subtrees is 20 times 10. I claim. So I don't understand quite how that recursion works. Okay, let's just try doing this. Let's just try just doing the absolutely ridiculous, okay, let's try, when in doubt, just bash it with computation approach, which I don't like very much. Okay, I mean, it's just running it on 100 machines. Some of them are very slow. Look, so there's 3 left. There's 3 laggards there, which might be the Platonic solids. Does anybody know what that other peak is? Anyone want to guess what the other peak is? I don't know. It's around Theorem 360. Ah, come on, 2 left. Yeah, Bob is asking, are there algorithms to... There we go. Oh, good. Oh, silly me for... I shouldn't have printed it out. That was part of my mistake here. Okay, so now... Okay. Let's just get the sense percent 815. It's a pity they wanted different colors, but anyway, so we can see that there's a little bit of, it's growing a little bit. Okay, I have a suspicion that we're actually going to peak out soon. Let me just take a look at something here. So I'm somewhat optimistic that if we look at %816 and we do length / at %816, that we won't have... Yeah, the number of 6s I'm claiming is slightly going down here. So I don't see as many 5s as I would like. Still 403 that haven't converged. All right, one more try here. Let's just see how grim this gets. Let's try doing the 6th case. All right, but what I hope to figure out, okay, so, here's a few other things that I had looked at. I had looked at the relationship between the length of the proof as stated in English and the length of the proof as stated in our computational form, length of the theorem as stated in English. Now, I had also just started scraping the version in Greek on the grounds that it's a little bit more faithful to the original story. Let's see. Somebody's asking us trying this machine. It's just a bunch of machines that I happen to have that are pretty powerful, but I'm only running it on 100 CPUs. I could connect this to 1,000 CPUs. That would require me to and run it on a cloud server. But I kind of don't think that's going to help us here. I think we just need to algorithmically think through how to do this. There's got to be, there's got to be some simple way to do this. Given a graph, isn't it just one of these, depth first scan type functions. Oh, look, that's finished. Exciting. Okay. Look at that. 12,000, specific calls to the theorem prover, so to speak. Okay. And let's try doing last 6. Oh gosh, still a lot of places where things haven't converged. Well, I don't know how many. Okay, we clearly need algorithms here to do this. And I suspect that some of these results are going to be absolutely astronomical. So just to review, okay, so what have we learned here? So this is, let me just look at a couple of other things here. So I was curious about, so some of these are things like looking at lengths of statements in different forms. I don't know if the community graph plot is based on books. I mean, it doesn't have the right number of, how would we do a community graph plot? Anybody know how to label these to the point where, you understand what I'm saying? Let's see, does community graph plot allow us to specify the number of communities?
Not that I see. Oh, wait.
Oh, this is just a plot. So, but there's a community, there's presumably some function that I find graph communities. Oh boy, there's different things here. So by the way, this one thing we should also do is to plot, given the layered digraph embedding of, hold on one second, where, look. Okay, so now here we want to say vertex size, arrow, and then some betweenness centrality or something like that. We can certainly do vertex size is vertex in degree. Is that going to work? I don't know if that works. Let's just try. Is that totally broken? Or does it do the right thing? Well, I'm not seeing anything huge there, so let's just see how that, anybody know how this works? May I look it up, please? Well, clearly we can do it like this. Vertex size goes to hash arrow, vertex in degree of EUC comma hash. Map that over vertex list of EUC. This may look really stupid. And then we could try doing betweenness centrality. Oh, look at that. That's cool. Okay, so that's showing us which theorems here, although we think actually the reverse graph might be the better graph. Do you agree? The reverse graph here. So if I say reverse graph, there, I don't need to change the in degree here, right? Because that This will just change the embedding, the layered digraph embedding, right? It's not going to change which vertex is in which order in the vertex list. So it's still 3 and 3. Because I'm only reversing. Okay, so that's showing which theorems in Euclid have the most immediate, okay, so most immediate sort of use by something else. So now, let's say, between this centrality, what the heck? Why is that doing that? Between this centrality, oh, for all the vertices, okay. So then what we want to do there is vertex list, you see arrow between the centrality, and then I want to say there, I want to thread that. I don't know whether this will, I don't know what the values of the between the centrality are. They may or may not be sensible. Splat. Okay, let's say 0.05 times the between the centrality. Yes, it will be nice to label the larger nodes. Let's do that. Okay, so there's some nodes that get few direct contacts, but are very popular otherwise. Okay, let's see if we can label the nodes. So let's say vertex label arrow, and then let's say if vertex in degree of UC comma hash is greater than 20. Actually, what I want to say is hash arrow. If vertex in degree of hash is greater than, I'm guessing on the 20, then placed, and then let's put just the label placed of hash comma center. Otherwise, let's just say none. And then I want to map that over vertex list of UC. And then I want to do this. And then the only other thing I want to do here is I'm going to compress this a little bit. So I'm going to say this thing, let's just do this. Let's say row of that subbook, and I know it's going to give a bunch of errors here. Sorry about that. Comma dot. What was it called here? Theorem again? Is that right? It's called
Yes.
Theorem. All right, drum roll. Let's see if this works. And let's see if it's smart enough to put the label in front of the thingy, or whether it's going to do something stupid there. Come on. Oh, there we go. Okay. Yeah, it's got some messiness at the top because I didn't do this correctly. All right, what's 10.11?
Comparing lengths, if I remember.
Can you look it up?
Looking at.
This is kind of cool, actually. Really is kind of cool. Okay.
If 4 magnitudes are proportional and the first is commensurable with the second, then the third is also commensurable with the fourth.
Okay, what's 1.31? That's a winner of Petrinus centrality.
To draw a straight line through a given point parallel to a given straight line.
Weird. Okay. So we clearly, I mean, what we should do. Okay, so this is already kind of interesting. And I mean, so what we're learning here is, okay, let's pull this back a bit. What we're learning is the intermediate theorems matter. Without that, you're dealing with exponentially many, applications of the common notions and postulates. That's hardly surprising. That would be like saying in our multi-way system up here that back up here, that we can dramatically reduce the path length by adding in intermediate lemmas. But we don't have an a priori procedure for deciding. In other words, Euclid made the choice. I'm going to call that theorem 1, book 1, proposition 8 or something, right? That is the thing that we ask ourselves, which ones of those are worth naming, right? Of all the possible lemmas here, of all the possible subpaths, which ones are worth naming? And can we, for example, find an optimal collection of subpaths that will optimally, I mean, again, it's a self-fulfilling story, because the things we want to prove are, if we wanted to shorten every path, okay, which are the paths that are most worth compressing in order to shorten the average path? Do you understand the question? Right.
So between two between two formulas here, you'll have many paths, and you want to find a lemma that decreases the average length of the path.
Exactly.
In an optimal way.
Yeah, right. Exactly. So in other words, we're asking, given that we make a big picture here, let's say out to 8 or something, given that we make one of these, what will be, if what we want to do, if we want to find, if we are tracing all possible paths, which lemma is most worth introducing to shorten the average path, right? So we could do that by simply asking, okay, for in this thing, we've got this multi-way system, okay? And so now what we could ask, I mean, I don't think this is the best example, actually. I've got a better example. Hold on one second. I had a better example. Where is it? I had a better example. It's from the NKS book, actually. Oh, that was the out components, by the way, for a much simpler theorem. Oh, this was the thing where I was looking at all possible paths. Look at that amazing Gaussian. That's looking at, yeah, it's looking at all possible paths. And this was the thing that I wanted to get right, which I didn't get right here. This was looking at some kind of backbone, which I think is also a thing that we can look at for the existing. I'm not completely sure what this is. Okay. Anyway, oh boy, I had a better, yeah, so William on a live stream is asking, what's the analog of lemmas in space? Yeah, I mean, these things, and there was a question earlier about if proofs are like histories in physics, histories have amplitudes, what's the equivalent of amplitude for a proof? So that's an interesting question, because I mean, these are a quantum superposition here would be a collection of terms here, which are, I think that's where model theory comes in, because I think when you coordinatize these things, you're essentially foliating this graph and you're defining that some of these things will be considered as equivalent for purposes of a particular model. Yeah, Richard is thinking that Gaussian is interesting. I thought that initially, but I think it is just the central limit theorem. I think it's just a path counting. I think it's just that it's essentially a binomial path counter. Okay, but anyway, if we're tracing all possible paths, which lemma is the most worth introducing to shorten the average path? So here, if we just say tuples of, let's say, vertex list of MW, comma 2, that will give us all the 2 tuples, right? And then for each of those, we would get the path length. So find shortest path. An interesting point, which I don't know whether we should take seriously or not, is that this is a directed graph. So I'm kind of thinking I'm going to make this into an undirected graph for the time being, because I think that's a closer model for math. Okay, so let's make that into an undirected graph. Okay, so now let's say tuples of vertex list. So find shortest path in that undirected graph from, oh, piffle, let's have to do this, right? No, let's just do this. Hash sub 1, hash sub 2. Map that over these tuples, and that's going to give me the shortest path. Oh, silly. That's the shortest path. What I want is the graph distance, right? Oh, but these shortest paths will give me an idea about the lemmas, because those shortest paths, I want to find out what substring, what subsequence is most common in those shortest paths. Am I making sense?
Yep.
But this, if I simply say graph distance, okay, so this is now going to give me, so let's say I make a histogram. Okay, that's so by the way, this is the longest lemma, the longest proof. We're going to have to ask that question, but we can certainly ask for the mean graph distance, although that may not be the best measure, but that's a possible measure of what it means. You know, that's a possible lemma choice. Okay, all right, so now the question is, which of the possible lemmas would most reduce that value, right? So for every lemma, we could simply just introduce the lemma and do the computation again. It's a little grotesque. Should we do that, or should we try and, we could just do that to just see what happens. Or we could try and compute it from this. Can we compute from this what lemma is going to most reduce things? It's which subsequence is most common in here, isn't it?
Sounds good.
Yes.
How would we get that? How would we figure that out? Well, here, let me, while we're thinking about that. Let's do the stupid thing, and let's just take this where we're computing. So we say with MW equals okay, so here we want to say append oh, there's another issue. There's another issue. Look, because this is not an undirected graph. The thing we made, Oh, this is more complicated because this thing, we cheated. At the end, we made that undirected, but that's not the right thing to do. What we really want to do is to say reverse, I think. I don't know whether it's going to give the same result. Let's find out. Can anybody see how this is going to work? If I say join this to reverse / at that, do you understand what I'm trying to do here?
No.
Okay, so I'm putting in the okay, so I put in, oh, now I want to say undirected graph, simple graph of undirected graph. Now do you see what I'm doing? The question is, am I going to get the same result as this? And I believe I'm not. That's really weird. What's that BB doing there? Oh, that's BB goes to A. Right, because I had it the other way around as well. You see what I'm doing? So I'm trying to make this a two-way graph, and then I'm removing the two-wayness of it.
BB is not in the first graph.
Yeah, I believe it's not in the first graph because the vertex list will be different. Right, the vertex list will be different in the two cases. Right. So in fact here, this is the reversible MWR graph. And so if we look at MWR, how is that going to differ here? Mildly different. Yeah, I mean, it is definitely different. So that's what we'll have to do. So let's look at MWR here. Okay, so slightly longer mean difference. Okay, so let's take a look at this. And what we're going to do here, this thing there, is we want to say join to this the, hold on, join to that the new axiom, new ax. Okay, so with this, with that MW, closes there, that's the mean of graph difference. Oh, actually, this is not, I don't need to do this. I could say graph distance matrix. Instead of all those tuples, I can just say graph distance matrix, and I can just say mean of flatten of graph distance matrix. Correct? And then n of that. Okay, now, new axiom. So this is now, well, let's just do function new ax. Oops. And let's just apply it to the trivial one. Okay, that's our 3.86. Terrific. All right, now our new axiom would be the tuples of the vertex list of MWR. I have a feeling I may need to do this on all my machines. Let's just do it. Okay, so this is going to let's see, parallel map monitored. All right, let's see this go. What the heck is that? Help! Machines are dying. Okay. Okay, I feel stupid here. Why are these all the same? Oh, stupid, stupid, stupid. Yes, that's why they're all the same. Okay, here goes. No, what's going on here? Oh dear, I have a bad feeling I can't kill these. This is what I get for running 100 machines. Okay, let's see what happens here. So this is the tuples of that. Oh, very important point. That's wrong. That's what it should be. Very frustrating. We're going to have to kill this off, and I'm going to have to probably kill the remote jobs. It's very annoying. Well, let's see. There are various physics comments on this live stream. I apologize for the fact that I've been looking at metamathematics here rather than specifically at physics. This is sort of an application of the formalism that we have, and also, for me, a way to understand better kind of the significance of that formalism. Let's see if we can make this work, and I'll respond to someone's asking about, is there a description of the I-100 machine? So it's very boring. It's just a bunch of machines with a bunch of cores connected in the most uninteresting way. The more interesting thing is to watch us actually run Wolfram engines on something like AWS, which I'm not doing here. Oh, what did I do wrong? Help! Oh my gosh, idiot. I'm an idiot. Embarrassing. Dumb. That should be an append. See, this is the problem. If I was just running locally on this machine, it's a no problem if the whole thing goes splat, because I can just stop it. But by the time there are 100 machines running, it doesn't work as easily.
Yeah.
So it goes. All right, let's see if we got this code right. Anybody read this code and tell me if it's right? All right, so remember what we're trying to do here is find what are the lemmas which are the most beneficial lemmas. Of the 6,241 possible lemmas, which by the way, we could prune by a factor of 2 by we could prune by a factor of 2 by looking at the reverses of all of them. Could prune possible lemmas by a factor of 2. And that is not a great sign that this thing is slowing down. Look at that. Its ETA keeps on increasing. Ah, splaff. No, machines are dying. Who knows why? Maybe they ran out of memory. Okay, there they go. No. It'll restart automatically on each machine. Okay, so it says resurrected as Threadripper. That was resurrected as kernel ID 96. Well, it's still running. Let's see what's happening. It's predicting another minute and a half, but I don't believe it, because look at that. It's bogged down at 3,800. I wonder why it's going so slowly. Why is it so difficult for it? Oh my gosh, I know what's happening. Oh my gosh. Okay, here's what's happening. As we have a lemma, we get further in space, so to speak. We get further out in metamathematical space. And once we're further out in metamathematical space, 8 steps can lead to a huge number of terms.
Makes sense.
Right. So in fact, what we have to do here, this is really probably completely doomed. And it's probably going to blow the memory out of all these machines. All right, this has to be done a little bit more carefully. So wait a minute. Could prune lemmas by a factor of 2. Also, oh my gosh. You see, this is even eating my current machine alive. Well, if this goes down, if this whole stream goes down, we'll know why. The machine got eaten alive. We'll be back if it goes down. It's supposed to not. Oh my gosh, my mouse is. Can you still hear me? I don't know whether you can still hear me.
Yep.
My mouse is dying. I don't know whether its preemptive scheduling is working correctly so that it can still get out. It's not supposed to use up all the cores. I think this machine has 40 cores or something. It's not supposed to use all of those. Let's see. Also, I just should kill this. This is doomed. This is utterly doomed. Help. No, my machine is dying. Help. Yeah, it's a bad sign. I mean, that we can't even get, it's been 2,000 years. You would think we'd be able to figure out. No, actually, we're not doing Euclid anymore. This is just abstract systems. But this is asking the question. Okay, so there are a couple of questions here, which I think are good questions, which is there was a question from, what's the analog of lemmas in ordinary space? So we are compressing. So let's see, each geodesic here represents as a time-like curve. What is the analog of a lemma? What is the analog of a lemma? Let me think. I mean, you're basically changing the underlying laws of physics, because this is saying normally that this is the kind of process of going through physics. I think when you introduce a lemma, yes. The introduction of lemmas is analogous to changing the foliation. So I'm going to claim that introducing a lemma, I'm going to claim that there's a most obvious reference frame, which is just to go progressively down this picture, but that as soon as you introduce a lemma, you're effectively changing the foliation through which you're exploring the space. I think that's the correct analogy. Introducing a lemma is like changing your foliation. So I think because I think introducing a lemma is the beginning of turning this into a model, because a model would coordinatize every point. And I think that's the beginning of that process. Now, there's a question. There were some questions here about Brian saying the lemma of geodesic. Yeah, a lemma is the geodesic in the original system, but once you introduce a lemma, you shorten a lot of paths. Look, there are a couple of things that are quite confusing here. One is these multi-way graphs are the analog of our essentially quantum mechanical evolution processes. Space in our usual model is manifest in essentially the lengths, the inner structure of these things here. These strings don't have a heck of a lot of inner structure. If we were using something more obviously mathematical, like trees here, like expression trees, then it might be a little bit clearer. In our actual models of space, we'd be using hypergraphs here, which are not something that we normally use in representing mathematical objects. We could, but we don't usually, if that makes sense. Right. So in other words, this here is just a string, which is equivalent to an associative, something where the concatenation operator is associative, like an element of a semigroup. But you know, in a more general case, we can do something more like what we do with axiomatic theory. You know, what we do with something like this, where we have binary operators, for example, binary and unary operators here. And so one of the things I was trying to do was to actually look at, if we take the Boolean axioms and we make a multi-way system from Boolean axioms, what do we, so in other words, you can think of these as substitution rules, right? And we can ask, how do you grow the theorems of Boolean algebra from these axioms? Just like we're growing these multi-way systems from the axioms of the multi-way system. And then somebody was asking, can we do that for geometry? And the answer is, let's see, you can look at, can look here, and we have, I hope, handy dandy Euclidean plane geometry. Those are the axioms. Let me pull those in actually just for a second. Let me just take a look at them, just to see how complicated they look. Because remember, for Boolean algebra, we thought this was the simplest set of axioms, but in fact, I think they're just called this. Let's see. But in fact, that's enough. Right? So we thought this was what we needed for Boolean algebra, but actually that's enough for Boolean algebra. So the question is for geometry, what are the minimal axioms for geometry? And one thing I would like to try to do is to look for this axiom system, is to basically make its multi-way system and see how, you know, because this axiom is going to imply a certain set of equivalences between expressions for Boolean algebra. And I'd like to then see what, you know, of those, where are the, for example, I have just a list of the like 14 famous axioms of Boolean algebra. And the question is, where do those lie in this multi-way system of possible generated results in Boolean algebra?
It might not work as well, because one of them is through 2 points, there's a line. You can't really construct anything unless you have some sort of basis.
You mean in Boolean algebra?
In geometry.
Okay, hold on. Let me pull something in here for 1 second. I'm going to pull in the NKS book. Hold on, where is it? NKS book, original construction notebooks, chapter 12. It's always satisfying to see, you know, this stuff. Let's see, chapter 12, section 10, is that right? That looks promising. Those are all of the figures in this. I don't want to, so this now is asking for, oh, actually, here we have axioms. This is more promising. So axiom systems, I think this was a Matthew Sudzik production from long, long ago, and Matthew is on the phone, which is encouraging. Matthew, still remember this? Okay, there are the axioms of okay, so those are the axioms of geometry. I don't know what those are. So this is the current form of those axioms, it claims, at least here. Now, unfortunately, that seems to be an axiom schema down there. So in other words, that's a generator of infinite set of individual axioms. But this here is the set of axioms. So that's to be compared with, I mean, if I take say these axioms, whoops. Oh, I didn't mean that. I meant this. Okay, so that's what those axioms say. And the corresponding thing here has got all these things in it. But this is where there implies is here. Are these meta symbols, or are these things which are actually part of the language? So Ed is making the comment, you can't tell what the heck is going on if you just do it symbolically. But I think that that's true of any of these axiom systems. This is a purely formal axiom system.
Those look like the Hilbert axioms.
They are. So what's your point?
It's that it's hard to construct if you can't draw a line.
Do Hilbert's axioms not contain drawing a line?
Oh, I think it does.
It must do, because it has a betweenness.
Axiom of segment construction.
Where?
It's halfway down.
So that says there exists an x1 and b. So that's betweenness. That's a ternary operator. For which c, I wonder what c is. Maybe collinearity? So that I have a key to what it is. Segments are congruent. It's a congruence operator. Okay, so the interpretation of that is its congruence. That's betweenness. So it's both between and it's congruent. And there exists an x1 such that this is true. So anyway, I mean, look, the bigger picture, and we should wrap up in soon here. Yeah. So Richard on our live stream is commenting that this is the assembly language of mathematics. Absolutely, this is the machine code. This is kind of, this is right down in the machine code of mathematics. And the thing that is remarkable is that it looks like the machine code of mathematics and the machine code of physics are the same. And so what I'm chasing here is to use physical ideas like the ideas of general relativity and the ideas of quantum mechanics to understand the structure of mathematics. And what is the structure of mathematics? The structure of mathematics is the metamathematical space of all possible theorems and their connections. And the connections between those theorems are the progressive evolution. So in mathematics, what we're looking at is this is a network of, well, this isn't quite theorems. This is a network of the paths are theorems. Okay, so the paths, it's like in physical space. Let's see, in physical space, those paths are time evolution in this case. So that the theorem of mathematics in this interpretation of theorems, right? The theorem is saying this state turns into that. That's a theorem, basically. That's the analog for physics. The physics analog of the mathematical result is this turns into that in the over time. And what we're saying is mathematics. So what we're observing is that in physics, yeah, I mean, so it's a little bit complicated because in physics we see repeatedly this thing that we create turns into that, but this thing we create is a tiny subgraph of this giant hypergraph that represents all of the universe. Whereas here we're looking at a different case where, I mean, I could add in this case, I could choose to add in right here. If I go back up here, I could choose to contextualize rather my experiments, my math experiments, by adding a bunch of data to each end of each string. So that's the analog of saying, I'm looking at a physical system, I'm looking at a physics experiment that's being done in a subset of the universe. So my whole universe might be a giant string with 10 to the 100 elements, but I'm merely looking at this particular piece of that string. And that's the analog of doing that thing in physics, doing an experiment, a local experiment in physics. So what this is saying is, given that local experiment, given these axioms, which are rules, essentially rules of the universe, this system, this subsystem of the universe will evolve in this way. That's what this is saying. So each one of these paths is a statement in physics that says this turns into that, right? So the theorems in math, it's got a lot of background noise. Perhaps it's in there. Theorems in math correspond to which are of the form A turns into, or is equivalent to, turns into B, is the exact same thing as in physics. It's, A evolves to B, which is also like turns into B. So in other words, the role of the mathematician is in the math case, it depends on how Platonic you want to get. Either the network of mathematical theorems already exists, or the mathematician is exploring that network of mathematical theorems. Now, the next question is, in the mathematics that we've done, where do we choose to go in metamathematical space? Right? In physics, we can say, what experiments have we chosen to do? Or where in physical space have we chosen to go? We don't have a huge amount of choice about that relative to the whole universe. But it's like, what experiments have we chosen to do? And that's like saying which, and when we do an experiment, kind of we set things up in physics and they just do what they do. In mathematics, when we do an experiment, not using a computer, so to speak, we have to actually follow through and see what happens. But there is an inexorable there's an inexorable sequence of things that happens. But the question is, so what this is like in quantum mechanics, this would be like saying, we've got an initial state. These geodesic paths in mathematics are the analog of transition amplitudes in quantum mechanics. So each theorem path is like a transition amplitude for quantum mechanics. And so in quantum mechanics, we know that there's this notion of, the key question is, in that path, how does that path turn in branchial space? And that determines the amplitude of the quantum amplitude for that transition. And the question here is, what is the meaning? So branchial space is the space of entanglements at a particular, so if I did this, for example, if I said here, it's probably not going to be that exciting in this case, but if I were to say this, I bet it's not too exciting in this case. Okay, it's rather uninteresting. It's almost a complete graph. What that's showing is the set of relationships of entanglements between terms. What on earth is that mathematically? That's asking. So do you understand what this is doing? This is saying two nodes are joined if they have a common ancestor here. So this is in a sense saying these are two different outcomes. There are two things that would both be possible endpoints of a theorem. So the question then is, what is this entanglement graph that, this is throwing us into mathematics. Mathematics is about what theorems are true. Metamathematics is more talking about what are the possible proofs. Is this making sense? Anybody?
Yeah,
I think so. The paths on the left are proofs.
Right, paths on the left are proofs. These here are essentially a part of higher order proofs, because they're saying, given if you have two proofs of the same theorem, right, you can ask, what is the relationship between those two proofs? But actually, this isn't even proofs of the same theorem. This is proofs of nearby theorems. This is asking, what's the map of nearby theorems?
Right.
So what we're saying is, if we were to bucket, this is an interesting point. In a quantum measurement, what we end up doing is bucketing nearby quantum states. We have no direct analog of that in mathematics. Right? Our coarse graining in mathematics. Okay, so what is the analog? So that would be like saying we've got a collection of possible theorems that are nearby theorems, and what on earth are nearby theorems in mathematics?
Mathematical subjects.
Well, unless that's axiom, unless that's different axiom systems, but okay, nearby theorems might be about similar things, I suppose. There's another way to think about nearby theorems, which is things that are easily lemma accessible from a given, in other words, given a term, there are things that you can, there's a sort of a ball around that term that are things that are easily reachable.
Yes.
Right. So I mean, so there are a bunch of lemmas. So some theorems are shortly provable from others. Start with a bundle of quotes nearby terms, aka things which are, for which the proof of equivalence is easy.
As a consequence, Fermat's last theorem is proven.
What do you mean?
That was Andrews Weil's statement at the end of his proof of the. I can't remember the name of the conjecture, but a consequence of it was Fermat's last theorem.
So what? How does that relate to this?
It's sort of nearby. It was a very powerful conjecture, and the Fermat's last theorem was a trivial consequence.
I see what you're saying. I see. So you're claiming, so a powerful conjecture is something which is a big backbone, right? A powerful theorem better be a big backbone in this graph, right? Of which there are corollaries. I mean, basically, yeah, these might be called corollaries. The nearby theorems are basically corollaries. Corollaries. Brian is saying nearby theorems are ones that use similar lemmas. Yes, that's also true. Ones for which most of the proof is similar. But I claim corollaries may be the right way to think about nearby theorems. So we have a collection of corollaries. And one thing we're asking is, again, it's so confusing between these paths and complete theorems. A collection of corollaries are probably a bundle of GD6. Yes. So in a sense, the question of whether this is a positively or negatively curved space, for example, is a question of whether the corollaries at the two ends are closer, whether in the middle the GD6 converge or diverge. So in other words, whether these corollaries are, whether in the middle of proving these different corollaries, you end up with totally different paths to prove them, even though at the end they're very similar. Yeah, I mean, this is a little bit confusing, but trying to understand what well, it's a question, can this be seen as related to category theory? Yes. but it is, yes. And I mean, the whole, this is like a weak, I mean, you can think about these, I think, if you wanted to, you could think about the structure of this as being like a weak category with these one-way paths, or this is like categories, but I haven't done there's no transitivity here. I haven't made the transitive closure. If I made the transitive closure, which is what you would do in ordinary category theory, then I would basically have made every lemma. Right? So in other words, in category theory, the version of this would be that this graph, you take the transitive closure of this graph, which means that I am letting it be one step only to get to everything. But what's the relationship to category theory there is once you have that, these paths are proofs, but now you can look at the homotopy between paths, that is the transformation from one proof to another, so-called higher order proofs. And as you look at that, that's the analogous to higher categories. And the infinite limit of that is this infinity groupoid object. So, Jonathan has a bunch of conjectures about how that works and how it relates to the, I mean, Grothendieck studied a lot the limit of higher order, infinitely high order proofs, effectively, or what boil down to infinitely high order proofs. That is, yeah, so that's somewhat the relationship to category theory. Let's see. I mean, the issue, yeah, there's people are commenting here that this is running right into the arms of set theory. Boy. Okay, so here's a conjecture which is still a little bit fuzzy. Oh boy. This is, okay. There's this property of causal invariance, which is really important in the physics because it's what leads to general relativity and it's what leads to objective reality in quantum mechanics. And it's basically the statement that even though you may have two paths here which diverge, no divergence is ever final. You can always get back to where you were. You can always, you know, like this path here, it goes, you know, you go to ABAB, you might say, oh my gosh, I've got lost here, but actually you can always get back to ABAB. Okay, so the question is, in metamathematics, so causal invariance has significance for the physics interpretation of these things. What is the significance of causal invariance for the metamathematical interpretation of these things? In other words,
is that like the law of excluded middle?
I'm not sure. I don't think so. I think it's like the extensionality axiom, which is in fact Euclid's first common notion. And so the extensionality axiom says two things that are equivalent to a thing are equivalent to each other. See what I'm saying? So if these two things here are equivalent to that thing, then this is kind of saying that they're equivalent to each other. Maybe. Does that make sense? I mean, this is what critical pair lemmas and theorem provers are using, is that extensionality idea. Two things which are equal to a particular thing are equal to each other. Now, I don't know whether, I mean, the conjecture would be that somehow that assumption is what leads, okay, so one of the big mysteries of human mathematics is that there's so much that can be done without running into undecidability. And so I've been wondering about this for like decades, of why is human mathematics as doable as it is? Because in the computational universe of possible programs, you know, your average question is undecidable. Does this halt? Does this not halt? All these kinds of things. It's typically undecidable. In mathematics, the business of mathematicians has been to prove theorems, and they've proved lots of them. And you don't hear you don't see mathematicians on an average day tearing their hair out because they've discovered the thing they were trying to prove is undecidable. Right? It's actually a very rare endpoint for mathematics that people say, oh my gosh, this thing we were trying to do turns out to be undecidable. It's happened only a limited number of times in the history of mathematics. Word problem for groups, Hilbert's 10th problem, I don't know, maybe homeomorphisms of manifolds beyond 4 dimensions, or 4 dimensions and beyond, things like that. But there are comparatively few examples where things mathematicians have profoundly wanted to do turned out to be undecidable. And that's, to me, surprising. And so a possible hypothesis is that that fact that things don't end up being undecidable is some consequence of a fundamental assumption that is made in setting up the axiom systems for mathematics. That if you pick an arbitrary axiom system, that you would no longer have that feature, but that if you pick an axiom system that, for example, has this causal invariance property, which I think is equivalent, to the extensionality axiom, which is basically in every axiom system. It's fundamental to the way equality works. But I think, that might lead to the idea, that might be what leads you to, by the way, in set theory, there's an extensionality axiom, which is a much fancier extensionality axiom that works for infinite sets and so on. So the hypothesis might be, okay, the meta hypothesis is that in physics, as computationally bounded observers of the universe, we have to bucket certain nearby states together in some sense. That's the nature of our insofar as we are not able to sort of do enough computation to sort of break all those pieces apart. And the hypothesis would be that something similar happens in mathematics, and the cause is because of the assumption of this extensionality thing, which might have to do with, I just don't know yet, how it relates to equality and things like this. But so, in other words, the building of mathematics on top of set theory, which has this extensionality axiom, might be building on top of something which builds in a not too much undecidability, which is the same. Yeah, let me see. That's the same reason that we are able to derive 20th century physics, which makes statement about the universe which are not mired in irreducibility and undecidability. That we can make global statements like Einstein's equations and things without having to say, oh, let's take a look at what happens at the elementary length scale and so on. So that's So by the way, right. I think yeah, right. So there are various comments here on our live stream about should it be possible to describe the multi-way graph using lambda calculus? Yes, this multi-way graph is closely related to combinators and lambda calculus. I might talk about that another time. We're heading for the 100th anniversary of Moses Schoenfinkel's invention of combinators, which was the first example of a computation universal system, although it took at least 16 more years before anybody understood what he'd done. But yes, in December 1920 was combinators, which is sort of the precursor of lambda calculus. And indeed, these multi-way graphs are the evaluation graphs of combinators or lambda calculus. And so there is a relationship there. And it's Brian is commenting that perhaps it's self-selecting that our mathematics uses provable axioms. So you don't know from the axioms. The axioms, well, okay, that the axioms, my claim that extensionality axioms are important. Yeah, that may be true. I've always thought that the theorems, that the way we choose to explore mathematics is by keeping to situations where theorems can be proved. In other words, that how we generalize things in mathematics is not just, oh, we'll pick an arbitrary axiom system or we'll pick an arbitrary theorem to prove. We are always moving on a path that maintains, I guess the point there, yeah, viewed in these terms, all that's saying is we've already proved a bunch of theorems and we never go out on a very long prong here. That's what it's basically saying. Yeah, that's the statement, that in mathematics, you're usually not, your average theorem doesn't go that many steps. So in other words, unless you have a bunch of theorems already in the bag that allow you to get to your next theorem without too many steps, you just don't go there. I think that's actually right. So the claim would be, oh, this is a mess of a notebook. You know, the basic claim would be, in actually doing math, you don't go on a long path. You use theorems you already have, and go on a fairly short path. And that probably, yeah, so I mean well, that's basically just saying you only get to things that you can get to by fairly short paths. There might be things where there could be an arbitrarily long path, it could be undecidable, but you'll never see that because you're only getting to things that you can get to with fairly short paths. Okay, well, anyway, let's see, I'm looking at comments here related to the fact that classical mathematics is not constructive if we use intuitionistic logic. I don't think that we get to the Curry-Howard correspondence and we can essentially run into issues of undecidability. I think Curry-Howard is deeply burnt into all of the things we're doing here. Curry-Howard is basically, the Curry-Howard correspondence is basically a specific case of the statement, everything is computation, everything is equivalent. Type calculus is equivalent to logic, is equivalent to lambda calculus, is equivalent to computation. So I don't think, and I think this question of undecidability is a what you choose to look at question. In other words, programs often run into undecidability. Math usually doesn't. And that's something I'm still trying to understand. Well, so there's this question. Yeah, right. So Bob is pointing out, he likes the idea of calculating how much a theorem is worth by seeing how much it shortens paths. Okay, so this question of whether a theorem is worth something. See, here's a very interesting, surprising fact that I discovered, I don't know, 20-something years ago. Okay, this is, no, that's not the right page. This is the theorems of logic written out in lexicographic order with the theorems that are given names in logic textbooks highlighted. And the remarkable thing that I found is that those theorems are precisely ones that can't be proved from things earlier in the lexicographic list. So it's as if the analog for Euclid would be, if Euclid were to write down all theorems of geometry in lexicographic order, the ones that Euclid has named or has called out are precisely the ones that can't be proved from earlier ones in the list without going back. So eventually you've reached the axioms here. Yeah, so I think that's manifestly not true for Euclid, right? So, but because In the case of Boolean algebra, you're simply asking, as you aggregate theorems, most of these early theorems are very simple and don't yet have enough information to give you the full axioms. Right. So if Euclid's axioms in lexicographic order occurred later than many of his theorems, then the same thing could happen. But if his axioms are short compared to his theorems, then this idea is toast, so to speak. So anyway, the surprising fact that the things that are considered interesting in textbooks are kind of the minimum statements of their, they're the minimal statement of what they say. Yeah, so I mean, Bob is commenting, it should be possible to make a program to find interesting theorems. Yes, that is a very interesting question, whether you can do that, because one of the things I wanted to do to make a pure math version of Wolfram Alpha is, you type into Wolfram Alpha, if I just go to Wolfram Alpha and I type something like, tungsten, for example, I will just get interesting random facts Wolfram Alpha wants to tell me about tungsten. I have always wanted to be able to type in some piece of pure mathematics. Let F be a, let G be a group such that blah, 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 and then have it just tell me interesting theorems based on what I typed in. And so to be able to automate answering the question, what is interesting, would be highly interesting. Because in a sense, that's, so, okay, so there's a question here. There's a couple of questions from Bob here. There's one statement, it's hard to remove complex numbers from quantum mechanics. That's what I thought too. What we realized is the magnitudes are really a separate story from the phases. Actually, Jonathan just wrote a nice bulletin about how you can get quantum interference by understanding how that works. So it really isn't true. It's actually angles and magnitudes. So there's a question here. Yeah, could one generate Euclid's books programmatically? Interesting question. Okay. Richard is asking about prime theorems that are not decomposable. So I think the prime theorems that are not decomposable are the axioms. I think that's the only, what does it mean? Let's think.
What is the notion of decomposition?
Yeah, well, right. It's what can be proved from what. So you can circulate around, because what you choose as the axioms is, it's not clear what the basis is. Because, for example, in my Boolean algebra thing, I've got the sort of lexicographically simplest axiom, but I could use that. I could prove that from other axioms. So I don't think there's a notion of primeness, because I think you can always just circulate it around. There's a minimum basis in a sense, but there are many such minimum bases. And you can ask what is the shortest minimum basis, and that's what I was doing for Boolean algebra. Yeah, I mean, by the way, people are commenting on the nature of automated proof. I mean, automated proof is not a panacea. Let's be clear about that. In other words, automated proof is actually quite useless at some level. Automated proof is only useful for knowing what's true. I mean, I talked about that. I had this long blog post about explainability. And, this is basically, okay, there's my cool Boolean algebra axiom, but this is its proof. And I have no idea if this is the shortest proof. I was thinking, could we mount a giant distributed computing thing to actually enumerate multi-way systems to find out the shortest proof of my Boolean algebra axiom? Because this is like a 100-step proof, I think. And I bet from the playing around that I've done with our theorem prover compared to sort of minimum length things, I think it's at least a factor of 2 longer than it should be. But this proof is incomprehensible. And it's been 20 years and still nobody understands any part of it, basically. And we can see, is this the, yeah, I think this is a proof of part of it. This is the lemma structure of a proof of part of it. See, this is what I'm trying to understand is why, to what extent what we see here is a consequence of the way the theorem prover works, and to what extent what we see here is a consequence of the structure of metamathematical space. That's one of the questions. And then to what extent is, there's this metamathematical space of all possible theorems out there. As we explore it in doing human mathematics, what can we say about our sort of path of exploration? Yeah, well, you guys have just given me a huge amount of homework. This is terrible. Or not, as the case may be. But yeah, sorry, you were going to say something.
I think the exploration is also not just proving new theorems, but refactoring your axioms.
It's an interesting claim.
Like we were studying numbers long before Zermelo-Frankel set theory. It's almost like a refactoring the base code that you were using.
Yeah, that's arguably true, right? And we get to use, I mean, in a sense, so one question is, when we have different mathematical abstractions, do they correspond to using different, I mean, I think different abstractions correspond to yet something we haven't even talked about, which is, transforming this language into something different. Let's see. So a question from Marcos here: is the basis for Boolean algebra shorter in category theory abstraction? I don't know how you would do this in category theory. I don't know. This is an equational axiom system. I don't know how that works in I don't know. But I mean, okay, so you're talking about, yeah, I mean, is, the refactoring of axioms, what is the relation to abstraction? I have a feeling abstraction is more related to the refactoring of the representation.
I can see that.
Okay, so the question from Richard: the observable universe of metamathematics grows at what rate? In the things I've looked at, it's all exponential. So it's like an inflationary universe. And one of the questions is whether it develops cosmological event horizons. That is, whether there are parts of the graph, the metamathematical proof graph, which are separated from other ones, so that you are effectively, is that essentially speciation in mathematics, right? So, yeah, this is an interesting question, actually. This is sort of speciation in math, event horizons in the multi-way graph might correspond to the breaking off of different fields of mathematics, in which you don't have you don't have mutually provable things, if that makes sense. You have a different clump of proofs in one direction as in another. Okay, you guys are convincing me. This is a very interesting subject, this whole business about, I think, kind of a question in all of this. An example of a big question is, why is there so little undecidability in mathematics? Another question is, what is the limit of mathematics, right? Mathematics itself is always talking about limits, but what's the limit of mathematics as time goes to infinity? What does it look like? In other words, as mathematics kind of proves more theorems, does more stuff, what's it going to, my guess is that it's going to develop more and more general abstractions, but I don't know quite how that works. And I don't know what an abstraction is in the context of things like these multi-way graphs. And how does, that's the, in other words, forget. So in a sense, when we talk about infinity, we're not bothering to count all the numbers, 1, 2, 3, 4, 5, up to infinity. We're just saying there's this symbolic thing called infinity. But yet, when we talk about mathematics, we think we're going to do all the mathematics that we have to do in the future of our civilization, so to speak. We can't just say, consider the infinite limit of mathematics, which is a little weird. Given that in mathematics, we are perfectly well able to talk about, the transfinite ordinals, et cetera, et cetera, et cetera. It's like, why can't we just do that for mathematics itself? Just say, imagine the limit of mathematics. Now, what do we get? And the limit of mathematics is the limit of these multi-way graphs. And the limit of these multi-way graphs is very much like physical space. And so that's, in a sense, anyway, this is, it's a weird set of connections. Yeah, right. So there are questions here about there's various things about adjacency matrices. I have looked at some of those. I don't think they're all that interesting. We could look at these here. Heisenberg-Weil algebra rewrites rules over graphs to basis vectors. I do not know about that. I have to look that up. So different description languages, Markos comments, are certainly related to to other things here. Coxeter projection of a mathematical space, one can visualize the boundary. Interesting question. Bob is commenting on Roger Penrose talking about the end of time as a new Big Bang. I wish that we'd been able to reach Roger. Roger has not been well, apparently, which is really upsetting. Hopefully, he will reappear soon. Well, finding the limit of mathematics is certainly computationally irreducible. But it's still the case that we should be able to make, see, that's what's really interesting about the physics case, okay? You might think that when we have 10 to the 400 nodes in our universe, that we wouldn't be able to say anything, that we'd have to just trace all those nodes and see what they all do, et cetera, et cetera, et cetera. Yet, we have big statements we can make about the universe, like Einstein's equations, like we can predict, we throw a projectile and it'll go in a definite direction, those kinds of things. So even though there's all this complicated, irreducible stuff going on at the lowest level, there's still, at the largest scale, there's still regularity. And that's what I'm trying to figure out in metamathematics. What is the analogous regularity in mathematics that is analogous to 20th century physics, basically? That's the question. And is that regularity, in fact, related to, I think that the comparative absence of undecidability is a sign that there is regularity. But then the question is, what is the statement of regularity in metamathematics? That is the analog of things like Einstein's equations. And that's what we've been sort of looping around on. Yanis is commenting, the limit of math is about what we don't know, something not applicable to the universe, but that's not right. You see, the universe progresses through time, and we think we can say things about the future of the universe. And that's why I think we can say, and the universe has been around a long time, right? The universe might have had, in our models, it maybe 10 to the 100 time steps effectively. And that's a lot more than the amount of mathematics that's been done in human history. And so, but, so in other words, we get to see the aggregate effects in physics better than we get to see the aggregate continuum limits in mathematics. But the question is, what does the continuum limit of mathematics look like? And I bet that we've already seen, even in Euclid, I bet we see some features of that continuum limit. What are they? How do we understand what the sort of fabric of mathematics is? This question of whether physics is a special case of mathematics, I actually think that the end result is that physics is a representation of all possible mathematics, and that the physics that we experience is merely a slice of this rulal space that we talk about that corresponds to the slice that we can readily understand with our senses, so to speak. And I think that's directly analogous. We can do the same thing for mathematics. There's a space of all possible mathematicses, and any given axiom system is but a slice through that space. So there's a mathematics of all possible mathematicses, but we can already study this limit before we even get to the limit of all possible mathematicses. We can study the limit of a particular axiom system in mathematics in its limit. And by the way, I don't think the limit's going to be that different, because all these axiom systems are computation universal, among other things. I don't think, for Bob is commenting, is the mathematics related to the universe that we live in. I think the answer is if we allow hypercomputational mathematics, which basically means things like it's like Turing's logic based on ordinals and so on. If we allow hypercomputational mathematics, then we get something different that we can't reach concretely from our universe. But yeah, anyway, all right. I can see that people have lots of questions and comments, but I need to go to a different meeting and I need to get some dinner. It's that time of day in my part of the world. Yes, I'd love to go on talking about this. This is, and you guys have, as I say, one of the pieces of homework you've given me is this Metamath thing, and I'm hoping somebody has sent me the a link to a version that we can download the structured form of it, and then maybe we can grind it up and see what its metamathematics looks like, as well as old Euclid. All right, I better go, but thanks to local people, and thanks to people on the live stream. Gosh, I wish I was hoping I was coming to the end of my study of metamathematics, but I'm realizing it's a big and deep subject, and I'm a little bit afraid that, I mean, we have these applications of the physics project to distributed computing, to metamathematics, potentially to biology, and potentially even more bizarrely to economics. And I'm getting a little afraid that each one of these is going to turn into a giant monster. But I find this stuff really interesting. So that's good. All right. Well, thanks a lot, guys, and see you.